Welcome back. On the last few videos we have seen how to reduce second order linear partial differential equation, how to reduce into linear partial differential equation. We have seen in the last two videos we have seen how to reduce second order linear partial differential equation, how it is reduced to a canonical form, and we have shown with an examples with constant coefficients. The examples that we have considered are equations with constant coefficients, and so this working with these constant coefficients is relatively easy to get the canonical form. So in this next one or two videos we will see how to reduce equations with variable coefficients. So those a, b, c, d these are functions of x and y. So if we consider them, how to reduce them into those equations with the variable coefficients into canonical form, so that you can reduce the equation into a simpler form, so which some of the equations can be solved, okay, and some you may not be able to solve at least in the canonical form. So we will see how we do this. We start with an example that is a hyperbolic equation. So let us consider the equation examples. We will consider three examples. One is reduce the PDE y square uxx minus x square uyy equal to 0. So domain is nothing is given, so that means basically xy belongs to R2 into canonical form. So this is the question. So we will solve it, give the solution. So we will reduce how to reduce we will reduce this equation into a canonical form. So the moment you see this one, first you like earlier, like we have done earlier for the constant coefficients equation, you just check what is a is y square, b is 0, c is minus x square, d, e, f, g are all 0. So we only have to say this discriminant b square minus 4ac is 4x square y square. This is if you consider any domain x square y square, if you consider any of these domains. So you see this, this is actually full domain, okay, you have a full domain, and discriminant is 4x square y square. This is always positive if x y is non-zero. So that means you remove this from the plane, you remove these coordinates, Cartesian coordinates, this axis, okay, coordinate axis if you remove, that is the domain. That means this is one domain, this is the domain you are dealing with. So you have to consider this equation in each of these domains. This is not new, as we have seen in the Abel's formula in the ordinary differential equations. If you know one solution y1, to find the other solution, you found the Abel's formula, you can find the other solution, other linearly independent solution from the Abel's formula. Y2 is given in terms of y1 into some integral x0 to x in the integrand involving y1. There, because the 1 by y1 square is involved in the y2, so it has to be, y1 has to be non-zero. If y1 is 0 at certain points, you can remove from the domain and consider the ordinary differential equation in separately in each of the domains, and then get from the Abel's formula, because Abel's formula makes sense only when y1 is non-zero. And then once you get your y2 in each of these domains, and you can take the limits, and at those points also, at those points at y1 is 0 is also you can get, because y2 is continuous. So actually y1 y2 both are both make sense in the even at the points that are removed. So in the same way here, even though if you want to reduce this equation into canonical form on the coordinate axis, because x is 0 or y equal to 0, 4x square y square is, which is 0. So when it is positive, that is in each of these domains, this is clearly hyperbolic because it is positive. But if it is 0, it can be possible on the coordinate axis if x y equal to 0, this is 0, okay. So this is what you have. So in this case this is parabolic. But to see, this is a partial differential equation, and the domain here is just x equal to 0 and y equal to 0, this coordinate axis. This is one dimensional domain. So, you have a partial differential equation in a one dimensional, does not make sense. Okay. So, just like ordinary differential equation, if it is given at one point, so it does not make sense. So, the same way here partial differential equation should be defined on a at least in a plane domain if you have two linearly independent two independent variables. Okay. If you have two independent variables for the partial differential equation, the domain should be a plane domain, but here this is not a plane domain, one less dimension, that is simply lines. So, those you can ignore. Okay. So, in that sense the equation you say that is hyperbolic rather than saying parabolic at these points. Okay. So, equation that is well defined only in these in these domains, in these quarter planes. Okay. In these quarter planes you have equation is well defined, it is hyperbolic. So, once you have this hyperbolic, you know how to find those new variables xi and eta. So, from this differential equations, ordinary differential equations, that is b is 0, b plus square root of b square minus 4 is, that is 2xy divided by 2a. So, 2y square. So, this is simply x by y. Other differential equation is dy by dx is b minus b is 0 minus square root of b square minus 4a, so that is 2xy divided by 2a. This will give me minus x by y. So, if you solve these two ordinary differential equations, what you end up is the new variables. So, if you do this, what you get is y dy minus x dx equal to 0, and this becomes y dy plus x dx equal to 0. So, this will give me y square minus x square equal to constant C1, and similarly this will be y square plus x square equal to C2. So, you will get actually y square by 2, that 2 you can absorb into the arbitrary constant, so which I am calling C1. Okay. Similarly here you have y square by 2 plus x square by 2, that 2 I can absorb into the arbitrary constant. So, from this you can get your new variables, xi is a function of xy, eta is a function of xy, that is y square plus x square. Now, what you need to reduce this equation, that involves uxx and uyy. Now, just calculations part, start with ux. Ux is u xi xi x, that is minus 2x u xi plus 2x u eta. Okay. U eta, eta x is, eta y is eta x is 2x. So, here 2x, here minus 2x from xi. So, this is equal to minus 2x u xi minus u eta. Okay. So, this also gives me what is my dou x. Dou x is actually, so what is x? X you have to write in terms of xi. So, what is x? X is square root of, so x is eta minus xi by 2, that is x square. So, once you take the square root, that is your x. So, finally you get minus 2 square root of eta minus xi by 2 into dou xi minus dou eta. So, this is my dou x. Once you know this, you can get your uxx. Uxx is dou x acting on u. So, this if you write it, minus 2 square root of eta minus xi by 2, okay, and then you have u xi minus u eta. Okay, first you write this dou xi, dou eta. This is my dou x. Now, dou u by dou x you can pick it from here. So, that will be again that into this into minus 2 x is square root of eta minus xi by 2 into u xi minus u eta. Okay. You take this minus and minus, that is going to be plus, and 2 you can write it here as 4. Okay. And this 2 also you can cancel and write finally 2. Okay. So, root 2 into root 2 is divided by, that is 2, 1 by 2 into 4 is 2. So, this you can write the square root of eta minus I into this, and similarly here eta minus I under root. So, this is what you have to expand nicely. This as you are assuming that this is one function, this is another function. So, you differentiate with respect to xi and eta, the product of these two functions. So, if you do this, you get 2 times square root of eta minus I, and what you get, dou xi of first function, that is minus 1 by 2 root of eta minus xi into u xi minus u eta plus, now I differentiate this one. So, this will be as it is, eta minus I, now u xi minus u xi eta. Okay. So, this is what is your one part. Okay. This is actually, that is what is the first derivative, this derivative. Now, you have to take the minus, now differentiate with respect to eta, this product of two functions. So, you will see that that will be that will be 1 by 2 square root of eta minus I, and you have a minus. Okay, this that minus comes out, and after in the differentiation you do not get any negative sign. So, you have this into u xi minus u eta, and the last term is minus this minus and the square root of eta minus I. This will be u eta xi minus u eta eta. Okay. So, this is what is the final form. So, if you now simplify, what you end up is, you take this 2 goes, this goes, and here also. So, you collect these terms. This one, what you see is these are same. Okay. So, this one and this one are same. So, what you end up is 1 by square root of eta minus xi u xi minus u eta. So, with minus, so you have a minus sign, 2, this cancels, what you end up is u xi minus u eta, plus, now you take this one. So, 2 times square root of eta minus xi into eta minus square root of eta minus xi is 2 times eta minus xi into u xi minus u xi eta, and here again if you multiply this here. So, this 2 times eta minus xi out, and what you end up is minus u xi eta, u eta xi, u xi eta both are same. So, you have u eta xi minus that is minus plus u eta eta. Okay. This is what you have. So, finally, this you can combine it together. So, this is because u xi eta equal to u eta xi. So, you can write this as 2 times u xi eta. Okay. So, this is what is my u x x, everything in terms of new variables xi and eta. Now, what is my u y? U y is, again if you do same way, u y is u xi y, that is 2 y, plus u eta y, that is also 2 y. So, 2 y is common, u xi plus u eta. This is equal. So, now what you need? Is what is y? Y is actually from, because you know what is xi and eta, y will be sum of this. If you take this xi plus eta by 2, that is your y square. So, square root of xi plus eta by 2 is my y. So, if you write this, square root of eta plus xi by 2, okay, into u xi plus u eta. So, this gives me what is my dou y. So, once you know that, you can write u y as dou y is now 2 times square root of eta plus xi by 2 dou xi plus dou eta acting on u y is here. So, this is into 2 times square root of eta plus xi by 2 u xi plus u eta. Now you combine this together, so you have 2 times this 2 goes. Okay, the denominator will be together 2, 1 2 goes. What you end up is this dou dou xi plus dou dou eta, this operating on square root of eta plus xi and u xi plus u eta. Okay. So, these are two functions, product of two functions, and this is the operator. So, this is how you have to look at it. So, this will give me 2 times eta plus xi. Now, you differentiate this on this product of functions, you get 1 by 2 square root of eta plus xi into u xi plus u eta plus square root of eta plus xi u xi plus u xi eta. Okay. And then now if you differentiate with respect to eta, you get again 1 by 2 square root of eta plus xi into u xi plus u eta plus square root of eta plus xi u eta xi plus u eta eta. Now close the bracket. So, you have these two are same. If you combine it, it is going to be 1 by square root of eta plus xi into u xi plus e eta. So, together 2 times u xi plus u eta. Now, this one if you combine this you see that eta plus xi, this into this will be 2 times of that, and what u is common is u xi plus u xi eta plus here this is also same. So, you can see that eta plus xi into eta plus xi, that is 2 times eta plus xi into u eta xi and u xi eta both are same. So, you can combine it together with 2 plus u eta eta. So, this is what is my u y y. So, these are the only things I need, because I do not need u x y, because the given differential equation is this one, that does not involve mixed derivative u x y. So, put together you combine it and you see that u x x y square into u x x minus x square u y y equal to 0 becomes, what is y square? Y square is eta plus xi by 2 into u x x. U x x is, you can make use of u x x, that is this one. So, use this u x x minus 2 u xi minus u eta plus 2 times eta minus xi into u xi xi minus 2 xi eta plus u eta eta. Okay. So, this into this one. So, that is this part minus x square is eta minus xi by 2, okay, into now u y y, you can make use of this expression. So, you have 2 times u xi plus u eta plus 2 times eta plus I u xi xi plus u xi eta plus u eta eta. Okay, this ends, that is it. So, this has to be equal to 0. So, that is what is the equation. Okay. Now, you can combine these two. So, 2 cancels here, and what you end up, eta square minus xi square. Now, I consider this one into this will be eta square minus xi square u xi xi minus 2 xi eta plus u eta eta. Okay. And here if I combine this one and this one, after cancelling these two, you see that minus eta square minus xi square u xi xi plus 2 u xi eta plus u eta eta. what is left with these two. So, this will be plus eta plus xi into it is minus u xi minus u eta, and here eta minus xi into u xi plus u eta equal to 0. So, you can see that this is common. So, these terms will be 0, this gets cancelled. So, what you are ending up finally is minus 2 here minus 2. So, you have a total 4 eta square minus xi square u xi eta minus right. So, minus this if you write, that will become eta times u xi, here eta times u xi, that gets cancelled, and here if you expand it, you expand this and this, combine it. So, we will do it separately. So, you see that eta u xi minus eta eta plus xi u xi minus xi u eta. Now, similarly, you combine this one, minus I take it out. So, what is left with the plus one? Okay. So, what I am doing is this one, whatever in the brackets is this eta u xi plus eta u eta minus xi u xi minus xi u eta. So, you can see that these are cancelling. So, you have to write what is left with here. What is left here is 2 times eta u xi minus 2 times minus plus, okay, this becomes plus 2 times xi u eta equal to 0. So, you can divide it. So, finally, you get u xi eta minus you can both sides you can make it plus 2 can cancel, make it 2, and what you are left with is eta by 2 eta square minus xi square into u xi plus xi by 2 eta square minus xi square into u eta equal to 0. So, this is your canonical form, that is u xi eta plus lower order terms. These are your lower order terms, which is equal to 0. Okay. This is the required canonical form. This we cannot integrate. So, we know only one technique, whether we can integrate directly. So, which is not possible because it involves second order and first order terms. So, you cannot solve this partial differential equation even after reducing it to canonical form. Okay. So, this is a hyperbolic example. So, we will look at other example where we have seen how to reduce a linear second order partial differential equation into canonical form. The hyperbolic linear partial differential equation we reduced into canonical form in this video. So, we will do 2 more examples in the next video. So, in which we consider examples equations with variable coefficients for parabolic and elliptic cases. Okay. So, we have seen this example where the equation hyperbolic equation is reduced to this canonical form, which you cannot solve. Well, if you consider now some equation which is the typical equation is hyperbolic equation, that is a wave equation. Let us consider one more hyperbolic equation, for example uxx minus c square uxx. So, actually it should be utt. So, utt minus c square uxx is 0 and t is positive is the domain, x is in full domain. Let us say this one. So, this is an example 2 which is also hyperbolic equation. This is the wave equation, this is called wave equation. Okay. So, what happens? So, how do we know? We do not know how to solve this equation so far, whatever we know, okay. But because this is a partial differential equation in the domain t is positive, x is the full domain and t is positive. So, if you take this as a t, this is your x axis at t equal to 0 is your x axis, at every time t your domain is here, okay, at t equal to t, big T, something like this. So, the domain is upper half plane, but we do not know how to solve this, but let us see by reducing this into canonical form can we solve it, okay. So, if you consider here a equal to 1, b is 0, c is minus c square, okay. C is minus c square. What is here? Physically, c is the speed of a wave speed, and u is the amplitude, okay. U is the amplitude of the wave. So, we will see. So, you will consider the discriminant b square minus 4ac is actually equal to b is 0 again, minus minus plus 4ac c 4c square. So, implies this is always positive because this wave speed is always positive and 4c square is always a positive. So, it is a hyperbolic equation. So, that is what is we know, okay. So, what are the variables? What are the new variables that ODEs if you solve you can get them. So, dy by not dy by, so y is x here. So, you have to consider dx by dx by dt equal to b is 0 square root of b square minus 4ac, that is 2c divided by 2a. So, this is equal to c. What is the other equation? You have again dx by dt is minus 2c minus square root of b square minus 4ac divided by 2a. So, you have minus c. So, if you solve this you can easily see that x minus ct, okay, equal to c1 and x plus ct equal to c2. So, this is what if you solve these two ordinary differential equations. So, you consider this as your xi, this as your eta. Now, what you need? utt and uxx, you calculate them. So, ut, so start with ut, that is u xi into xi t. What is xi t? Minus c. Xi t is minus c plus u eta, eta t is plus c. So, together you see that minus c comes out, u xi minus u eta, okay. So, this is what is my ut. So, utt is from this you can get dou t, that is minus c which is a constant dou xi minus dou eta of ut. So, that is minus c times u xi minus u eta, okay. So, c common, so you have c square dou xi minus dou eta, just like earlier what we have done. This is acting on u xi minus u eta. So, what happens here? So, this will become c square. Now, you simply differentiate, you see that u xi minus u xi eta minus, now if you differentiate this with respect to eta, you will see that u eta xi minus u eta eta. Mixed derivatives are continuous. So, you have c square u xi minus 2 xi eta minus minus plus, this is actually plus u eta eta, this is my utt. What is your ux? Ux is u xi into xi x. Xi x is dou xi by dou x, that is 1, plus u eta x again is 1. So, you have simply this one. So, you have uxx is simply dou xi plus dou eta acting on u xi plus u eta. So, this is simply u xi plus u xi eta, that is similarly u eta xi. So, you have 2 u xi eta plus u eta eta. And if you combine this, you take utt, that is c square into u xi, or rather utt minus c square uxx equal to 0 becomes now this equation, the given equation becomes c square, now pick up utt, that is this u xi minus 2 u xi eta plus u eta eta, okay, minus c square times this one. So, that is u xi plus 2 u xi eta plus u eta eta equal to 0. Okay. So, if you see that, you can see that these are all cancelling out, same derivatives, only mixed derivatives that is remained, that is going to be minus 4 c square u xi eta equal to 0. Minus c then is 0. So, 4 cannot be 0, c square, because c is the wave speed which is non-zero, c square also cannot be 0. So, that means u xi eta is 0. So, this is your canonical form. Canonical form for wave equation in the new variables. So, these are called xi and eta variables, these are called characteristics. Okay. These are called characteristic variables, because along these along these curves x minus ct and x plus ct, okay, this partial differential equation actually becomes ODE, that you need not worry. So, just let us see. So, this is the canonical form for which now I can find the solution. So, how do I find the solution? You see that u xi first, which is, if you differentiate dou eta. So, what is this one? This you can rewrite dou xi of u eta equal to 0. Now, if you integrate, you see that u eta equal to some function of xi, where f is arbitrary, f is arbitrary function. Now, one more differentiation, u, then you get u xi eta equal to f xi into eta, okay, plus some g of xi. G is also arbitrary, where g is arbitrary function. So, this is the general solution of this canonical form. So, in the new variables u of xt, in the older variables u of xt is this eta a into f of xi, right, this eta into f of xi, is it no, u eta is f of xi, yeah, that is fine. So, this should be u eta, you are differentiating with respect to eta. So, this should be eta, okay. U eta is f of, so if you differentiate with respect to eta xi, then it will be u xi eta, this will be 0. So, your original equation you will get, okay. So, this should be function of eta. So, you have function of eta here. So, this eta you can combine in this, eta into f of eta x is another f is arbitrary function into another function eta, that will be another arbitrary function. You call this C1 of eta plus C2 of xi, call this g is same as C2. So, this is your okay, if you write this as the same xi and eta, you can say that this is your general solution, where C1 and C2 are arbitrary functions, okay. So, general solution, because you have two arbitrary functions involved in your partial differential solution of the partial differential equation. Now, in the older variables u x t, what happens? If you rewrite C1 of eta is C1 of eta is x plus ct, and C2 of xi is x minus ct. So, this is your general solution of the wave equation. In the old variables, your partial differential equation is this one. So, this is your wave equation whose general solution is simply two arbitrary functions, each function takes, one function takes x plus ct as the ordinate, other function takes x minus c t. Okay. So, this is your general solution. So, you can actually find general solution of the partial differential equation, which is a wave equation, once you reduce into canonical form. So, with this we will close the video, and we will stop here, and we will look at other two examples of the partial differential equations. Those are elliptic and parabolic case. We will reduce them, we will reduce those equations with variable coefficients into canonical forms in the next video. Thank you very much.